All right, next slide, please. So field research involves data collection within a natural environment, and this comes with the unique danger of wildlife. In locations such as Africa and Asia, lions are apex predators that pose a major threat, while hyenas are less of a threat, primarily feeding off of carrion while avoiding other animals. The safest decision to make when it comes to lions is to simply avoid them and their territory, but in order to do so, the researcher must be able to identify there's a lion in the vicinity, which is a difficult task to do, which is why our team want to create an animal sound classifier. Next slide, please. So the main question that we are asking is, given an animal sound, can we classify whether the sound is coming from a lion or a hyena? And the process that we'll do is we'll take an audio sound file, process it to obtain its mel frequency cepstrum coefficients, also called the MFCCs, and then feed this into a model to obtain our classification. Next slide, please. So to briefly explain what MCCs are, we have to understand two separate parts. First of all, humans are much more sensitive to lower frequencies compared to high frequencies. For example, a 10 hertz difference in the 300 hertz range is much more perceivable than one in the 1400 range. And as a result, the MEL scale was created, which relates actual frequencies to frequencies that we perceive. And while sound is also generally represented in the time domain, it can be represented in the frequency domain in a form called the cepstrum, and doing so helps characterize a sound and gives it additional details. And so what the MFCCs these are the coefficients of a cepstrum in the MEL frequency domain. And the real only important part to understand is that this last step involves a discrete cosine transform, which minimizes the covariance from our individual coefficients, which justifies its use as input in supervised learning. Next slides, please.
So this is the structure of our data processing unit. So it first takes a video URL and then uses YouTube DL to download the video as a .mp4 file, then uses FFmpeg to convert the file to a .wav format and cut it to a number of samples. The samples are all 10-second audio files. The samples are then converted to MFCC data with a function called convertMFCC, written by the team and with Python Limbrosa library, and stored as NumPy arrays. We then compute the first and second derivatives for the MFCC data, which Daniel will talk a bit more about it on the next slide.
So briefly describing the model, in total, we used 5 convolutional layers and 2 fully connected layers. And the first 3 convolutional layers were trained independently on our 3 features, the MFCCs, its first gradient, and the second gradient, so that the output from a single feature would be 3 one-dimensional tensors. We then stacked a tensor from each input such that we're left with 3 tensor matrices, each with a total of 3 rows. The first row belonged to the MCCs, the second row belonged to the first gradient, and the third belonged to the second gradient. And this was done to preserve the time-dependent relationship between our 3 features. Afterwards, we applied our final 2 convolutional layers, which resulted in 5 one-dimensional tensors. And after flattening, 2 fully connected layers were used with 85 and 10 hidden units respectively, resulting in a single output to which sigmoid was applied to get a value between 1, which indicates a lion, or 0, indicating a hyena. Next slide, please.
So here's a summary of the qualitative and quantitative results we obtained with our best model. So on the right-hand side, we have the training and validation loss and accuracy curves. From these plots, we can clearly see that our model is not overfitting or underfitting. And with batch size of 30 and at a learning rate of 0.0001, the model does not have significant improvement after 15 epochs. Next slide, please. So in the end, the accuracy we get for all data sets are over 95%. And the test data set we have is composed of 20 data samples in each class. We can see that from the confusion matrix that the model can classify all test samples from the hyenas class, but failed to classify 2 out of the 20 lions class. So in fact, if we inspect the signal form of these 2 cases, we can see that these forms actually process a similar form as the ones in the hyenas class. So it is possible that although our model has good performance classifying general hyenas and lion sounds, with the training data set that we have, it can still not distinguish these 2 classes if their audio features are very similar. Next slide, please. So there are several points that were crucial to the success of the model. One of them is the selection of the data set. So for the Limbrosa library that we use to extract the audio features, the length of the window which we want to apply the Fourier transform on, and the length in between these 2 windows will largely impact our training result if we set these values differently. And for each of the data sample, we would also want our input audio files to be long enough to extract enough audio features for the model to detect and learn from the patterns. Next, regarding the key features of the CNN model, kernel size and number of convolutional layers were important. So during our refinement process, we noticed that having 2 additional convolutional layers will not increase our accuracy by a great extent. So for the future potential of this project, we believe that with the current experience we have from this binary classification of hyena sounds and lion sounds, we can easily modify this model just a little bit so that it can complete a multi-class animal sound classification. And other improvements we can also do is to think about how to optimize our model when given a very large data set. Next, please.
So we will show a demo of our project, which is a video with classification done in real time. So as you can see, the classification is generated by our model and formatted as subtext.
All right. I think that's it, right? Yeah, that's everything. All right. Good timing. Interesting problem. I think I get the motivation. Maybe you didn't say it, but I understand that the one good thing to say is that hyenas are less dangerous than lions. So it's good to know one from the other. I like your description of the MFCCs by and large. I haven't seen one as concise as that before. A question I had about, you went into extraordinary detail about this. And you said one thing that you're independently training these things. I don't think that's correct, right? You have one loss that trains everything together. Is that correct?
As in the 3 kernels were trained on one feature only. We had like a kernel responsible for learning off each feature.
Sorry, but it's all trained from the same loss, right? What you're
yes.
Is that you just have them separately coming out here. You've separated them, so it's not independently trained, but you
I see.
Architected something separately. But you spoke in detail about choosing these things. How did you arrive at this? Did you get it from somewhere else, or did you slowly build it up somehow from a smaller thing?
Yeah, so I guess first of all, just selecting the number of MCCs we want, that was one of the parameters we tested, and generally the industry standard is around 12 or 13, so we experimented around that range. And after that, this model was something I created after doing the research on the MFCCs. The first model we created returned only a single tensor for each kernel, and this just did not perform at all. It failed to learn on our training data, so we increased the number of kernels that we had on each layer until we had improved accuracy.
Okay. I was curious, there was another hyperparameter that you talked about later on, the window over which you calculate the MFCCs. What window did you end up, a window of time, I think, is that right? Is that the correct statement? Yeah. What was the window that you used in time?
So we used 2 seconds in the end, yeah.
No, you can go ahead.
Oh yeah. So we first tried 1.5 seconds and it didn't work. We increased it to 3 seconds, it didn't work, and then we increased it to 10 seconds, and then this time our model trains pretty well.
Oh, 10 seconds! Wow. But how long is your samples? How many seconds are your your inputs? Roughly.
Oh, I mean the input is 10 seconds.
Okay, so you just do one set of MFCCs. That's it.
For each 10-second sample, I think we use Wendy, was it 0.1 second?
Okay,
that was 30 milliseconds by default.
Saying the opposite of what you said a second ago. So I asked, what window of time did you compute the MFCCs over? And you said it tried 1, 3, and then 10 seconds work. And now you're saying it's 0.1 second. Which is it?
I think for each window length, it is 10 milliseconds.
10 milliseconds.
Yes.
That's 0.01 seconds. Okay.
Yeah.
Okay. Fine. That you didn't compare to any baseline here of any kind. Did you have a baseline?
The baseline we used was the form of our model that used only a single kernel, and this didn't really train at all. It stayed at around similar to like 70 or 80% accuracy and just remained like that for all epochs. We didn't actually mention it in the slides though.
Oh, but 80% is better than 50%, right?
Yes, but there was no indication of training. So we might have just been luckily obtaining that number.
Huh. You mean you don't believe in your test set? That's what that says, right?
Does it?
Yeah. Like your test set tells you how well your model does in data it's never seen. So got 70% accuracy. Then that's, in some other parts of the ML world, people go yoo-hoo when they get 70% accuracy because it's trying to predict something really tough. So, test set is test set. It's the result. Okay, Imtihan, any questions, comments?
Yeah. So your data set description, I didn't see a mention of like the size or the time window per sample, same as what Jonathan was saying. And Daniel, because of your response to the last question, I want to ask, did you guys make sure to balance the classes?
Yes, there's a portion in our training where you can see how many classes are in each, and the training, validation, and the testing, and they're all equal. Make sure that they're all like.
And why did you need to convert from MP4 to WAV?
That I'll leave that question to Ken.
Sorry, you said convert from NumPy to what?
MP4 to WAV.
To
this to this.
Yeah, so we first, because the source we have are videos, and they are in generally are MP4 files, and then we use FFmpeg to sort of cut it.
He's asking why, actually.
Audios.
He's asking why did you need the wave format? Why couldn't you go to MP4 is video? You mean MP3? Actually, I'm not sure.
Because our original plan was to just process the audio like directly without using MFCC. So we sort of changed that in the middle. So we just use the same data.
Okay, so you don't know the answer to the question is what you're saying. It's good to. Actually, I'm not sure I understand the question, but what you're saying doesn't make any sense to me. So, can you make the question more clear, Imtihan?
Yeah. So you're doing a file conversion from MP4 to WAV, and I'm just asking why you did it. And like the simple answer is just you only care about the audio, so you convert from MP4 to WAV, right?
Right.
Just mentioning that in the presentation would make it more clear.
Oh, I see.
And one thing with the introduction is you say lion and hyenas are found in all of Africa and Asia. That's not really a correct statement. That's an overgeneralization. So you should be careful about what you're scoping your solution to a problem, what you're scoping the problem to be.
Okay, any comments or questions from anyone else in the class? All right, thanks.